said the real power of the normal random variables is the central limit theorem. So let's take a look at that. So now let's suppose we have a sequence of random variables which are identical and independent. So we can think about these as independent measurements that we're taking from some population or repeating some measurement, some repeatable experiment. We have x1, x2, x3 up to xn, but then we can keep going as far as we want. What happens if we take a sum of a bunch of these random variables? So we know what happens to the mean and the variance. Let's just recall. So if I look at the mean of a sum of random variables, let's say I equals 1 to n, that's the sum of the means. I equals 1 to n. I mean, one way to see that is just by thinking about this as linearity of expectation, right? The expected value of the sum of some variables is the sum of the expected values of these variables. And by definition, that's what we mean by the mean of these xi's, right? Okay, now on the other hand, I can look at the variance. So the variance of a sum of random variables. And we find that if these are independent, and you need them to be independent, but if they're independent, then this is the sum, then the variance of the sum is the sum of the variances. It's maybe the easiest way to see that is by thinking about it via covariance, and maybe I'll explain that afterwards. But in any case, the variance of the sum is the sum of the variances. Let's see what happens when you rescale a variable. That'll be another useful factor to recall. So just kind of in general, if I look at the mean of, I don't know, some multiple of a random variable, then by linearity of expectation, again, that pulls out. And what about the variance of a multiple of a variable? Well, that pulls out as the square. Okay. So, let's now think about this. What I can do is I can take, let's let x be the sum of these random variables I equals 1 to n of xi. Okay. And well, what's the mean of x? This is, well, this is the sum of the means, and each of the means is the mean of x. So this is like, so let's say each of these things has mean mu and variance sigma squared. So the mean of the sum is going to be n times the mean of any individual one, and the variance sigma squared x, the variance of x. Well, that's going to be, again, the n times the variance of any of these particular variables. So if I were to take x, and if I were to shift it by mu, and then if I were to rescale it so that it had variance, so shifting it doesn't change the variance, but now I want to rescale it to have variance 1, well, I should divide out by square root of n times sigma, because that would change the variance by the square of that, which would cancel off this term right here. So this is a random variable with mean 0, excuse me, and variance 1. And the central limit theorem says that this, as n gets larger, approaches the standard normal random variable. So central limit says that you could say this in terms of the cumulative distribution function. The cumulative distribution function of sum of the xi's I equals 1 to n minus n mu divided by square root of n sigma approaches the cumulative distribution function of the normal random variable z as n goes to infinity. So that is to say, what I really mean there is that if you wanted to calculate the probability of this random variable being less than some amount, you would be just looking at the same corresponding quantity for the normal random variable. So this is a really useful theorem. It basically says that the normal variable is the only game in town when you're making lots and lots of repeated measurements. And no matter how kind of difficult to understand or complicated your distribution of your individual, these individual random variables xi, as long as you aggregate enough of them together, the thing that you're going to be looking at is a standard random variable. It was a normal random variable, and after you kind of shift and rescale it, a standard normal random variable, and that's the same information. So let's do a quick example just so we can see how to use the central limit theorem. So in this example, we are fishing. We are catching fish in the river, and let's just say that typical fish you get, the mean is 5.3 pounds. Or no, it's a pretty good sized fish, right? So that's the typical fish that we're catching. Standard deviation we find is 1.2, or I guess maybe I should say that the variance is about, let's say, 1.1, right? The square root should be 1.2, so the square root, okay, 1.4, sorry. Let's just say 1.4 is the variance. Okay, and so what are we going to do? We're going to catch, let's say, I don't know, 10 fish. Let's pretend that that's big enough to use the central limit theorem in this case. Catch 10 fish, and we see how many pounds of fish that we have altogether, and we wonder, what's the probability that we have at least, say, 50 pounds of fish? So after we catch 10 fish, what's the probability that we have at least 50 pounds, at least 50 pounds of fish. Okay, so we'll let x be the sum of 10 identical independent trials, which in this case is catching a fish. So let's just assume that's identical independent. And so what are we interested in knowing? We are interested in knowing is x at least 50. And like before, we are going to, what we know about is really this variable x minus 10 mu over root in sigma. That's the variable that we actually know about. And we know that this thing is approximately the standard normal distribution. So what we're going to do then is just take this equation x greater or equal to 50 and tweak it to tell it in terms of the variable that we know. Of course, we know mu is 5.3, so 10 mu is 53. So x minus 53 is at least 50 minus 53 minus 3. And we then also know that 50 minus 53 over root 10 times sigma. Sigma was the standard of 1.2. That's going to be at least minus 3 divided by root 10 times 1.2. Gosh, I think I need a calculator. So let's see what that is. So that's, let's see, root 10, blah, 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 root 10 times 1.2. By 3 reciprocal 0.8. So this is like negative 0.8 0.8 roughly. Okay. And this is approximately our standard normal random variable, z. And so we're asking, really, what's the probability that the standard random variable, excuse me, is at least minus 0.8. So we want it to be, to the right, if we kind of visualize this for a moment, we have our little like nice bell curvy thing, which is our standard random variable. Its mean is 0. We have like, I don't know, like a standard deviation over here, which is, standard deviation, which is actually 1. And we're not quite 1 over. We're like here. This is, -1. So this is -0.8. And we're actually wondering what's the chance that we're in that zone on the right. And it looks pretty good, right? It looks pretty good. But to figure it out, I'd probably have to look it up in a chart. Can I find a chart so quickly? Here's a chart, 0.8. 0.8 right there. That is about 22, 21, about 21. So there's about like 0.21 on this side. And so that makes there about 79% roughly. Boom. Okay. Okay, so that's an example of how to use the central limit theorem.